So I'm going to talk today about electrolysis. I'm going to talk about alkaline membrane electrolysis, okay? And I'll tell you why we're particularly interested in alkaline membrane electrolysis. And I'm going to try to weave together our work on catalysts, electrocatalysts, understanding fundamentally how those things work, and how we've used that to design or work towards higher performance, higher durability electrolyzer systems, particularly focused on understanding interfaces. So you've probably seen this diagram. This is a diagram that shows how hydrogen made primarily via electrolysis from renewable electricity is critical for many different applications. Okay. I've made some modifications to this diagram, but essentially we need it for synthetic fuels. We need it for long distance transportation. We need it for metals refining. We need it to make fertilizer. We need it to use biomass. We need all these applications of hydrogen. This is maybe 20 to 30% of our global energy use. So batteries will be a big component. Direct electrification will be a big component of the energy transition. But hydrogen is central to many things that are hard to directly electrify and hard to store the size and the scale of energy with batteries. Right now, there are essentially two low temperature technologies that are commercial for making hydrogen from water. One of them is called alkaline electrolysis. And alkaline electrolysis operates in typically 30 weight%, about 6 molar potassium hydroxide. And it has between the anode and the cathode, here's the anode, here's the cathode, it has a diaphragm. And that diaphragm is a porous solid. So you can see the pores here. Here's the pores. And that porous solid is made up of polymer, typically a polysulfone, plus zirconium oxide. So it's an inorganic, organic composite, nanocomposite. And the pores are typically 100 nanometers to maybe 500 nanometers in dimension. The diaphragm is important because it allows you to get the anode and the cathode relatively close together and is flooded with potassium hydroxide that conducts the hydroxides. It has high conductivity because the pores are flooded with this high concentration of potassium hydroxide. The disadvantage of this system, though, is if you get the thinness too thin, if you make the diaphragm too thin, or if you have a variable electric load and say your rate of hydrogen and oxygen production goes too low, the crossover rate of hydrogen through these pores can become too high and you can get an explosive mixture of hydrogen and oxygen. This isn't a problem when these are running at their specified current density and with an appropriate thickness, but it does set a limit on how thin you can make the diaphragm and how variable the load can be. You'd like the electrolyzer to be able to respond to the grid cost of electricity on a very fast time. The other thing that's interesting about these alkaline electrolyzers and the advantage is that in alkaline conditions, you can use right now all earth abundant catalysts. So nickel, cobalt, iron anodes, nickel, moly, nickel, carbon cathodes. You don't need precious metals. So this technology is very scalable in that it doesn't use any precious metals. But because it runs in this concentrated KOH, because the separator is porous, and thus the crossover of hydrogen, it has some limitations. A newer technology is this proton exchange membrane electrolysis. Now, the key thing here is it actually does not have a soluble electrolyte. It runs in ultra-pure water. We don't need any supporting electrolyte because it has a membrane that is itself an ionic conductor. So here's an example of Nafion. This is what it looks like, a roll of Nafion. It's a polymer that's used in proton exchange membrane electrolysis because it has strong acid groups bound to a fluorocarbon backbone. And those strong acid groups create water channels that are inside the pores here of this plastic membrane. And those water channels have mobile protons in it. So this is a solid state proton conductor with very high conductivity. And because these channels are very small, the rate of hydrogen crossover through the Nafion is much lower than for the Zirfon separator. So this thickness here, that thickness can be less, and you can run these at higher current densities. So typically these are about 0.5 amps per centimeter squared typically, but these ones can go all the way to 4 amps per centimeter squared because you can use that very thin membrane that has low resistance. And on top of that, the ultra pure water allows you to have a much simpler balance of plant. So what that means is the piping and gas liquid separators, electrode wiring. You can use bipolar plates here easily without worrying about reverse polarization and things like that are a problem. Downside of this proton exchange membrane electrolyzer, though, is that at the anode, particularly where you make oxygen, the only catalyst that is stable there is iridium oxide. And even iridium oxide slowly dissolves and is one of the factors that limits the lifetime of proton exchange membrane electrolyzers. And iridium oxide, we only mine about 7 tons per year. And it's very expensive, about $5,000 per ounce. And an ounce is about, 30 grams or so, something like that. So it's very, very expensive material. So what we'd like to do and what we're working on in our group is combining the best features of alkaline electrolysis, liquid alkaline, with the best features of proton exchange membrane electrolysis, an alkaline membrane electrolyzer. And so it looks a lot like this electrolyzer, except instead of moving H+, we want to move OH-. And we need a hydroxide membrane to do that. So here's an example of schematic of what it looks like. It's very similar. This is a single test cell in our lab where you have an anode, a cathode, a membrane, and the membrane is a hydroxide conductor. And if this works, if you can drive efficient hydrogen production with this alkaline membrane, that allows you to use earth-abundant water oxidation catalysts and hydrogen evolution catalysts, so you don't need iridium. If you can do this and you can run it in this pure water feed to take advantage of this membrane-based architecture in a cell stack, this would be the ultimate electrolyzer. But it needs to work with very high efficiency, equivalent to the proton exchange membrane or commercialized alkaline, liquid alkaline system. And it needs to be extremely durable. Durability is a key factor in determining the ultimate cost of any technology. And so when we started out, we wanted to understand how to think about putting these systems together. And I'll tell you how we thought about catalysts and membranes and how we're learning from our initial data to design better systems and putting together a set of guidelines for building these things to last. So electrolyzers are very complicated. They seem simple, just 2 electrodes, but in reality, those electrodes themselves have many scales of porosity. So in the electrolyzer, let's take a look, for example, at the anode active layer. So you have an ion exchange membrane. That ion exchange membrane in this case is again moving hydroxides. And those hydroxides are moving across here to the anode. This region here is where the catalysis happens. So this is composed of catalyst particles and ionomer, which is mixed with it. The ionomer has to take the hydroxide that's coming out of the membrane and deliver it through the 3D porous electrode to the surface of a catalyst particle where the reaction can occur and you can make some oxygen. The oxygen then has to come out of the cell through what's called the porous transport layer, or the GDL, gas diffusion layer. And the electrons also need to transport out of the cell. So you need electronically conductive pathways for the electrons, and you need ionically conductive pathways for the hydroxides in this 3-dimensional porous electrode. All this is supported on this porous transport layer, which itself has a distribution of pore sizes, and these are typically sintered metals or metal fibers. So there's complexity at many different length scales. There's gradients in the water content, gradients in the electric potential, gradients in the pressure due to the formation of gases. And understanding and designing this is a major challenge. So if we could understand and design these 3-dimensional reaction zones and electrolyzers, we could make hydrogen technology much better. And we could also use these electrolyzer platforms for many other chemical transformations. So I'll start just telling you a little bit about what we know about the oxygen evolution reaction in liquid alkaline systems. This is historically where this electrocatalysis process has been studied. So this is, again, the oxidation of OH minus. So 4 OH minus, right, goes to O2 plus 4 electrons plus 2 H2O, okay? So it's this simple reaction, but this is typically studied in, say, 1 molar potassium hydroxide at room temperature. And we want to understand what is known and how these results from these liquid measurements apply to more complicated systems like this, where you have, for example, mobile hydroxides in a solid ion conductor, and you don't have liquid KOH electrolyte. So here's some of the data we've collected over the last 10 years. We found a lot of interesting things. The most active catalysts are not actually metal oxides. So if you have something like nickel oxide or cobalt oxide, what happens is you might have in your head a picture of the catalyst with some crystalline structure. It's a nanoparticle. But over time, it converts. And so it converts to these so-called layered double hydroxide structures. And the domain size of this ordered domain can be variable. So often people refer to something called an amorphous layer that forms on the surface of the catalyst. But what they really mean is locally ordered oxyhydroxide type structure, these layered structures. And that degree of order can be pretty small, so the domain size might only be some tens of atoms. And these are the active phases. The other thing that happens in liquid electrolyte, unless you really make a heroic effort to get all the iron impurities out, iron from the liquid electrolyte, iron from the KOH, 1 molar KOH, has a substantial amount of iron in it, and that iron actually can go in and substitute on the lattice at room temperature and activate this reaction, activate this oxygen evolution. So impurities are important. The actual phase is not the phase you think you start with, et cetera. But one thing we found that the catalysts that are good at this all have nickel, cobalt, and iron. Nickel or cobalt and iron. And they all form these active phases at the surface to varying degrees. And the effect is pretty substantial. So if you scrub all the iron species out of the electrolyte, this is the overpotential. This is where a perfect catalyst would start to make oxygen. Would be right here. This is current versus the overpotential versus the reversible potential. If you scrub all the iron out, you have a terrible catalyst. Nickel oxide is a terrible catalyst without iron around for making oxygen. But just a teeny amount of iron impurities and it's pretty good. And if you add iron intentionally, this is the world record catalyst still on a per site basis or per materials quantity basis for making oxygen in alkaline conditions. So it shows you that understanding the actual surface composition is really critical to how these catalysts work. And that's going to hold in all of our systems we're going to study. Another thing that's complicated by these materials is you have to move both electrons and ions. So if you go back to this slide here, right, in this zone, any electrocatalyst, it's not enough for it to have the right surface chemistry or absorption energies for the catalytic reaction. I also need to be able to move the electrons through the material. It needs to be electrically conductive. But metal oxides are not simple metals, right? They're often semiconductors or insulators. And it turns out that these oxyhydroxide phases, the active phases, these sorts of things, their electronic properties are very complicated. So you can go in and measure this. So here is the conductivity measured in what's called an interdigitated array electrode. So it has a film of catalyst with the gap between two electrodes. And you measure the conductivity as a function of the electrochemical potential of those electrodes, or the overpotential for driving oxygen. And what you see is that the conductivity for these phases is a log function, right? An exponential function, I should say, of the overpotential. So the conductivity is changing by orders of magnitude as you change the oxidation state of the nickel or cobalt. These materials are insulators in their resting state, very low conductivities, and they're conductors in their active state. And so understanding how electrons moving through these materials is also critical. And something that we have to engineer. So if we go back and we kind of look at activity trends, this emphasizes what I showed before. If you don't have any impurities, it turns out the iron phases are by far the most active catalysts. But for the mixed phases, if you mix iron active sites into nickel or cobalt hosts, these are all the champion catalysts that people make. They have the highest turnover frequency. But this is, again, all in liquid KOH, soluble liquid KOH. And how this works in our electrolyzers, it might be different. The iron is also dynamic. So Dongyoung Chung, he's now at KAIST. He was a postdoc when he did this work with Nenad Markovic. That's where I met him. He showed that the iron is dynamically absorbing and leaching from these electrodes. So these sites that are activating, you can see this. You can see the iron go on if you have iron in the electrolyte, and you can see that iron come off from the active sites. And so this dynamics is very important to understand. If you have an electrolyzer, and to get high performance, you need soluble iron. That soluble iron can go other places in your cell, for example, to the cathode, and poison it, maybe. So we need to understand all the dynamics of the soluble species, and iron is an important soluble species. These things are dynamic at the morphological level too. So here's an example. This is about 500 nanometers in dimension. This is an AFM image of a single sheet of that 2D structure laid on a hot G, highly oriented pyrolytic graphite surface. And if you do an AFM scan of this material as a function of catalysis, right? As you start driving catalysis, the whole sheet is breaking apart and the atoms are moving and reforming. There's a lot of dynamics going on. And so again, understanding those dynamics, which catalysts, which compositions are able to have a lot of mobility of the ions, which ones are more static, is important when you start talking about devices and building, especially these solid-state alkaline membrane electrolyzers. So we wanted to understand what we've learned for alkaline liquid electrolyte and see if it holds for alkaline exchange membrane electrolysis, where only the solid alkaline ionomer is present. So to do this, we first need to develop a good baseline system. So one of the challenges with AEM electrolyzer is, unlike proton exchange membrane electrolyzers, where anybody can purchase off-the-shelf components, iridium oxide, platinum and carbon, Nafion, dispersions, and membrane, and make a pretty decent proton exchange membrane baseline. In AEMs, there wasn't a good recipe or good membranes, easily accessible, or good baseline processes. So Grace Lindquist first started to do this in my lab and had to build up this baseline process. And so we looked at lots of different polymers commercially available. These are all what I would call second generation ionomers, AEMs. They have very good chemical stability. The older AEMs, the hydroxides would actually attack the backbone and cause degradation, so they would sort of self-destruct. But these new ones are pretty stable chemically to hydroxide attack. So these are ones that are commercially available, and here are their properties here, though I won't go through it. We started with these to screen. One thing you'll notice is there's a lot of conjugation in these systems. And a lot of that conjugated backbone stuff is built to actually help protect the system from hydroxide. So here's some performance data. All the polymers have reasonable performance. This Pipper ion, this structure here from Versogen, was the best, though we don't really understand exactly why. They all have very good conductivities. They're all, relatively similar conductivity, but it was the best. And, if we optimized it, we can get pretty decent performance, about 1.9 volts and an amp per centimeter squared with our baseline process. We're using iridium oxide as the catalyst. This is just because it's commercially available and stable. We're going to talk about non-precious metal catalysts in a moment. But, there's a couple challenges here. One challenge is that if I did the same experiment with a PEM, or if I just look and see what the performance is, I would be down here. So there's still a performance gap. We want to lower that voltage to be competitive with proton exchange membrane electrolysis. So how do we do that? The other problem is durability. Still a major issue. So here's some durability data. And our best one, again, is this piperine. We don't really know why they're so different, but they're all degrading way too fast. So the best sample is about a millivolt per hour of degradation. There's a fast component and a slower component to degradation. This is only over 180 hours. These need to last 10,000 hours plus, more, really, but that's sort of a minimum test time. So this is very short. And this amount of degradation is totally unacceptable. What we really want is 100 to 1,000 times lower degradation. We want to be measuring microvolts per hour, 1 or 2, 3 microvolts per hour. So what's going on here? Why are these degrading so fast? And these are only running at 0.5 amp per centimeter squared. We want to go to 2 to 4 amps, right? Where it's just going to get even worse. So if you look at this, so what we do is we take the cells and we peel them apart in very simple types of experiments. In this case, we're looking at the XPS spectra, X-ray photoelectron spectra. Here's what the piper-ion film, the ionomer we're using, the hydroxide conducting ionomer looks like. It has nitrogen. Nitrogen is this group right here. That's important because that's the counterion we exchange for hydroxide in the cell. That's the counterion to the mobile hydroxide. So you better have nitrogen there. Has nitrogen to start with, has a little bit of fluorine. That's because this particular ionomer has a little bit of fluorine on the backbone, though most of it's hydrocarbon. And it has carbon. And there's different types of carbon which you can fit and assign to their different energies in the XPS spectrum. But if you run it for 175 hours and you look at the anode, this is the anode, you see no nitrogen left. This is bad. You see fluorine peak much lower, and you see a huge amount of oxidized carbon. So this is telling you there's oxidative degradation at the anode. Probably those aromatic components in the backbone are particularly susceptible to oxidation. We can look in more detail. Here's a cross-sectional image. This is a focused ion beam, a cryogenic focused ion beam. This is the membrane here. So this is the membrane. And it has the mobile hydroxides that need to come up through here and react at these interfaces to make O2. Okay? And this is a little bit of a model system we built so we could get a nice clean interface here and cross-section this. We ran this for 100 hours, and what you'll see is dramatic. All these particles here, they've been washed away, and only the particles that are left pushed right on the membrane are here. And they're actually etching into the membrane. So what you're seeing the catalyst eating the membrane, eating the ionomer that was holding the film together and eating the membrane. So this is the oxidative degradation. This is a big problem we need to solve in these. So we'll come back to that in a moment. I want to talk a little bit more about using non-precious metal catalysts at the anode and how we can eliminate iridium oxide and performance opportunities there. So we've screened a bunch of metal oxides. These are all commercial. So we have now some that are custom built that are much better, maybe down around here in voltage, but it's not so important at this time. We can discuss that if you have questions. But one thing you'll notice, if you look at the polarization curves, cobalt oxide, nickel oxide, they're actually pretty similar to the iridium oxide. And a lot of the trends, the voltage we see at 1 amp per centimeter squared, can be explained actually by the conductivity, the electrical conductivity of these materials. So we measure their electrical conductivity ex situ in this case, because these are metal oxide powders. We know that their surfaces are transforming under reaction conditions, but we just, as a first line of attack, we measure the electrical conductivity just between two metallic discs in a pressed pellet configuration. And you can see that you need high conductivities to get good performance. If you don't have high conductivities, it doesn't work. But there's a bigger problem, and that's, again, the durability. Like anything with iron in it has actually really bad durability in this particular example. So we wanted to understand that also. These durabilities are similar to what I showed you before. Notice this is only 20 hours. We're still seeing significant degradation, though they're stable enough to study. They still have the oxidative processes going. So we wanted to tease this apart a little bit more. One of the things we've been using a lot, and I recommend people invest a little bit of time to set it up in their lab if they're working on membrane-based systems, is having a reference electrode, a real reference electrode. And the way we do this is pretty simple. It's been used in the fuel cell area to some extent previously. It's a little tricky to get set up, but we have a lot of details in our papers, and you can email me if you're interested in applying this in your own lab and having problems. But this is the hydroxide exchange membrane. You can kind of think about it sitting in this stack here with the cathode and anode electrodes sandwiching that membrane. We take a piece of that membrane and we connect it to the same material as a strip, which actually runs the outside of the cell. And so outside the cell, you can use a little glass O-ring joint, and you can put a real reference electrode and have a little potassium hydroxide in there. So this allows the reference electrode to actually sense the electric potential right here inside the cell because there's no current flowing through this. So we use this a lot now to have a real reference electrode that's sensing what's going on inside the cell, but integrated outside of the cell. So here's, for example, the total cell voltage measured in a reference electrode setup. And here's the fraction that can be assigned to the anode. And here's the fraction that can be assigned to the cathode. You see the cathode has a small overpotential, about 200 millivolts in an amp, but the anode has a pretty large overpotential, right? The equilibrium potential would be 1.2, so we're up here at least 700 millivolts above the equilibrium potential. You can also look at the degradation. And you see, again, big degradation at the anode, whereas the cathode's pretty stable. These are all things that are expected, but it's nice to be able to tease those apart specifically. We can also do impedance. So one of the challenges, if you're looking at the total cell impedance, it's complicated. You have a lot of humps. You have a lot of humps changing, semicircles changing with time as the cell is degrading. But what's nice is we can actually now do impedance with our reference electrode, and the equivalent circuits are simpler because we're only looking at either the cathode or the anode independently. So we can see the cathode arc measured with the reference electrode and the anode arcs measured with the reference electrode. And you notice the anode actually has two semicircles in it, which is probably representative of the degradation processes. You see this other semicircle growing. We can also take these cells apart and look at the metal oxide catalysts and how the oxidation of this ionomer is affected by what catalyst we use. And we found something very interesting. If we use iridium oxide, notice we have a lot of oxidation. That's consistent. Loss of nitrogen, loss of the fluorine. That's consistent with what I showed you before. Though if you use something like cobalt oxide, you see a lot less oxidation, but we're still seeing similar degradation. And one of the reasons for this is that cobalt oxide is a semiconductor, whereas iridium oxide is metallic. So iridium oxide makes really good electrical contact to all the ionomer, so it can oxidize ionomer everywhere, whereas the cobalt oxide, or I guess down here, this is showing nickel, cobalt, iron, but it's the same idea. If you don't have good electrical conductivity, you can only oxidize polymer that's near the current collector. So most of the polymer stays undegraded, but it doesn't do you any good. It doesn't help you, doesn't make your device more stable, because this region of the electrode is just simply not active for making oxygen anyways. So you have to be a little careful interpreting these data, as you have to understand what the electronic properties of your material is and how that affects the chemical changes you see in your anode. Another thing we found, which was interesting, is that when we took these fairly stable, but again, we haven't solved the durability, they're still not nearly durable enough, but these cobalt oxide anodes, and we intentionally added a little bit of iron. If this had been a liquid alkaline electrolyzer, the voltage would have gone down, would have activated it. But that's not what we saw. We saw actually enhanced degradation with mobile iron, just small amounts of mobile iron. So we have a feeling that dynamic iron coming on and off our catalyst is something we want to avoid. In the alkaline membrane system, this is different than the liquid alkaline system. The liquid alkaline system, it tends to activate the anode. Here, it seems to be deleterious, seems to be bad for durability. And we also have to understand how to design these cells to stop the degradation mode, especially oxidation. How do we stop that oxidation of the ionomer? So we looked at some different ionomers. Here's an example of an ionomer that's all sp3 carbon, no double bonds. This should be more resistant to oxidation. And we did the same types of experiments, but we saw still problems with durability, and we saw substantial oxidation and substantial loss of the nitrogen charge-bearing group. So it didn't seem to matter that we had all sp3 carbon. We're still seeing degradation. We went to fluoropolymers as a proof of concept. So imagine you take Nafion. Nafion is a proton conductor, but we can mix some Nafion into our AEM, and we can put it at the anode and see, does the fluorine CF2 bonds oxidize? And sure enough, if you run a Nafion anode in a proton exchange membrane environment, you don't see any oxidation, but in an alkaline exchange membrane environment, you do. So it looks like when you have basic media and alkaline conditions, plus the oxidizing potential, you can degrade CF bonds. Whereas in acidic local conditions, these CF bonds are stable at the same potential. It's probably because OH minus will attack the backbone if it's polarized under positive voltage conditions at the anode, and the local base is particularly aggressive on organic material. So what can we do? There's these different degradation modes. There's the nucleophilic attack mode of the hydroxide. This has been solved by designing the polymers. But these oxidation modes, particularly radical oxidation or direct oxidation, are something we don't yet know how to solve. And we need to think a little bit about how we design the actual interface between the electrode, the catalyst. This is going to be our cobalt oxide, for example, and our ionomer. And we know, in conventional electrochemistry, you have soluble ions, you have a diffuse layer, you have a Helmholtz plane, and you have some structure of the double layer. But what if all of this double layer is made up of polymer? How does that double layer even look? What is the double layer structure, and how do we control the processes here at this interface to prevent the degradation that we're seeing? So can we control, for example, where the ionomer is in the electrical double layer? Can we prevent this oxidation? Here's some data that's pretty interesting. So in this case, we're looking at our baseline system, and we run it in pure water, okay? And here's the performance in pure water, 1 amp per centimeter squared. This particular cell, it's about 2 volts at 1 amp. And then if we add a little bit of potassium hydroxide, this is what most people do in the literature, and they do that because it increases the performance quite a bit. So that potassium hydroxide helps conduct the hydroxides in that porous electrode, and it reduces the problems you have with the ionomer because you have a background electrolyte to conduct hydroxide, and the ionomer doesn't have to do all the work. But what was really interesting is not only did it increase the performance, it also increased the durability quite a bit. So this slope, this is much more stable than in pure water. And we could even increase the current, so the starting voltages were about the same, and still the durability was much better in the KOH cell than it was in the pure water cell. So what's going on? Why, when you have a KOH, just a little bit of KOH around, even running at very high currents with a very oxidizing anode, you see very little direct oxidation of the ionomer? You see much better durability, much better maintenance of the original features of the cell. Okay, so what's going on? Why is this? And so we've been thinking about this, and we think it has to do with the nature of the double layer. So if you have a metal oxide surface, this is our catalyst, for example, and that metal oxide under locally basic conditions, it's going to have some negative surface charge. And so this polymer here is going to be strongly absorbed onto that metal oxide. But if you add a supporting electrolyte, those negative charges can be screened by the potassium ions, we think. And that might move this distance of the polymer. It might move that polymer further away from the surface and therefore prevent the direct whole transfer, the direct oxidation process, because if this polymer is too far away, that tunneling process will be slow. We haven't proven this, but it's a hypothesis that's interesting. Can we, again, control these sorts of parameters And how do we engineer this? How do we engineer this type of system without using KOH? We'd like not to have KOH. This is an area that we're actively working in. So one idea is to actually build an interface that suppresses the direct oxidation. So here's kind of a schematic picture of what's going on. We think if you had a catalyst like iridium or cobalt or any of these catalysts, when they're trying to make oxygen, some fraction of the current is going to oxidizing the ionomer. We don't want this to happen. So how do we stop that? So if we could build a thin layer, here I'm showing HF, hafnium oxide, a amorphous hafnium oxide layer we've been studying, to passivate the electrode. And if it could be built so it's amorphous and had some pores in it, so hydroxide ions could move easily across this green layer or sufficiently enough, and if it was thin enough that the resistance of the hydroxide layer was not too high, so imagine this is 10 nanometers or something, it might prevent the direct electron transfer to the ionomer because this distance is too far, the electrons can't tunnel that far, but allow the process we want to happen. This is like an SEI layer in a battery. So this is exactly this idea. Can we create an artificial SEI? Can we make stabilized interfaces? And how do we use that? So this is an example of what we've been working on. So here's a porous transport layer. Here's some cobalt oxide catalysts. We actually have some much nicer catalysts now. I should update this. But essentially, we've started building catalysts directly on the fiber. So this is a stainless steel fiber in this direction, and then it's been treated to grow some cobalt oxide nanostructure on it. And you can change this nanostructure and change the loading. There's a lot you can do, but the idea is that we could take this nanostructure and then we can coat it uniformly with this hafnium dioxide or other things to passivate it. And so this is kind of the picture here. And let's look at some of this data. So let's look at the iridium data. So when we coat iridium oxide with different thicknesses, 25 cycles or 50 cycles. This is durability data. Here's showing from 25 to 150 cycles in the cell initial performance. Here's the polarization curve. You see the iridium without any coating is the best. If you put a thin layer, I think this is about 5 nanometers or 3 nanometers of hafnium oxide, you pay very little penalty in performance, but it does get a little worse. And it gets worse and worse and worse if you make it very thick. But then you look at the durability data, it's actually dramatically changing the shape of these curves. If you have just iridium, it starts at a lower voltage, but boom, it degrades very fast and before it stabilizes. And essentially what you're doing is you're eating up all that ionomer, and you have, this is completely unacceptable. If we put a hafnium oxide layer on, we're starting at a higher voltage, but the degradation rate is dramatically suppressed. So we certainly are engineering this interface. This is not a competitive cell. The voltage is too high. There's a lot of work to do here, but it's illustrating the point of how we can engineer this interface. Same thing for the cobalt oxide. Again, you see some substantially stabilized performance when you use the thin layers of hafnium. And here's the XPS evidence. You see a much reduced oxidation when you have this hafnium layer over the cobalt oxide as opposed to direct contact between the cobalt oxide and the ionomer. So we're excited about this approach. We're targeting many different approaches to stabilize these reactive interfaces, which we think are really central to making high-performance electrolyzers. So I'll just end with a few emphases, and then we're happy to open up to questions and discussion. To emphasize, alkaline membrane electrolyzers, they really need catalysts and interfaces that are designed very differently than liquid alkaline. Liquid alkaline is a very different type of system because you have soluble KOH, right? And that's very different. It's not the same thing. We need to rethink how we design these systems. Ionomer degradation, despite all the work in this field, and it's been beautiful new ionomers developed that are much more stable than they were 10 years ago, but it's still a major issue, particularly this oxidation. And we think SEI layers and engineering interfaces are the key to this. I showed you one example of passivated anodes where we built an SEI and we're starting to understand and make progress. We've also been working on electrolyte additives, so adding things to the ink to stabilize the ionomer, particularly inorganic components. If you really solve this, you get this durability solved, and you have sort of, I don't know, 5 microvolts per hour durability, and you want to run at probably 2 amps per centimeter squared at 1.8 volts. If you can do that, this is a home run technology. This could be incredibly cheap. It's going to be much better than liquid alkaline, much better than PEM, but it has to have both performance and the durability. And to do that, I think we need new designs and new understanding. And that's what we're working really hard to do with our team here in Oregon, and our team moving forward at Berkeley, and with our collaborators around the world and at various companies. So with that, I'll end, and happy to take any questions. So if you're really modifying the double layer here, you should modify it differently if this is lithium, sodium, potassium, right?
Yeah.
So we need to do that series. We haven't done it yet, but we'd like to understand how the cations are modulating that. But we'd also just like to get rid of the cations altogether, because you really don't want to have the cations. The soluble electrolyte gives you many problems, device overall system design. It makes it a lot more complicated. There's these problems when you for example shut down your cell, because you have these bipolar plates, so the cathode and the anode are essentially on the same piece of nickel or steel. When you turn the cell off, what can happen if you have electrolyte that's getting pumped through the cell, you actually can polarize your cathode in the wrong direction. So your cathode can get polarized positive and your anode can get polarized negative. And it has big effects on the stability of the system, of the catalyst. So that's one problem. So this is called reverse polarization. Another problem is the shunt currents that flow through these external paths in your stack, because you have this huge stack of bipolar plates in your electrolyzer design. So you'd really like to get rid of all the ion transfer. If you don't have any KOH and you only have ionomer here, this becomes a lot simpler. And that's what the PEM systems are like. So we think that we can learn from the KOH systems, but we'd like to get rid of the KOH and have only pure water, so we don't have these reverse polarization, no shunt currents. You can do all these other things that you'd like to do with a membrane electrolyzer if it's possible. Tom has a question about the main reason for oxidation at the anode, whether it's electrochemical potential or a chemical reaction. We don't actually know, okay? So it could be, right, if you imagine your anode and you had some polymer here, okay? And what's the oxidation? Well, the oxidation is going to be the transfer of an electron here, ultimately. So this would be direct, and there would have to be some tunneling process, typically like you'd have at any electrified interface. We think this is substantial, but it could also be that there could be some oxidation of some mediator, and that mediator could be like a radical species that is a metal ion, a dissolved metal ion. There's a lot of things that could, in principle, mediate that. So we could oxidize that first, and then that could diffuse away and degrade the polymer backbone somewhere else. This will be difficult to stop via our passivation strategy, but we need to understand those, and we don't understand the relative contributions of those yet. What happens if we directly extend the MEA to contact with liquid KOH instead of adding the sense strip to AM? This is about the electrolyzer membrane sensing reference electrode approach. The question is, why do you necessarily need to use a strip? Why can't you just make the whole piece of membrane bigger, I think, right? And we can do that. That works too. And then you put this on here. The reason we use the strip is because the membrane is expensive, and this uses a lot less membrane. So we can use a very small strip and it works perfectly well, as opposed to using a huge membrane every time. And the membrane is something like a sheet. It's like $1,000 or something. That's the only reason we do it. But we get the same information in both cases. The strip is affected by applied pressure. There's a lot of technical details getting this thing to really work reproducibly, but we have all those sorted out. Are happy to help people if they want to try. It says AM research is mainly focused on zero gap alkaline research. That's the question. I would say, it depends how we define that. So, but zero gap, you'll hear this a lot, zero gap. What this is referring to is actually this sort of cell here, liquid alkaline. So in the old days, some cells are made this way. They had a anode, a cathode, and a separator, and there was a gap here between the electrode and the separator. And that gap has some IR loss. It makes the cell simpler to fabricate in some ways, and it increases the distance, more space for bubbles to come off. But that IR loss is a problem if you want to run on high current. This is showing a so-called zero gap because the gap here is zero. Now, it could be zero gap with a diaphragm, or it could be zero gap more like a membrane electrode assembly. I would say both those are being pursued. So there is a community of people, and there's a huge opportunity space simply for getting better diaphragms, better electrodes, higher performance using liquid alkaline. Then there's a big community of people in industry and academia that are building cells that look more like these membrane cells. They're zero gap for sure. They're CCMs, catalyst-coated membranes or architectures, MEAs, I should say, membrane electrode assembly architectures. But instead of feeding pure water, they're feeding in water plus KOH, and so it's sort of a hybrid. I call this a hybrid. It's a little bit like the liquid alkaline cell because you have a lot of the liquid alkaline issues with the flowing KOH, but it has some of the advantages of the membrane cell in that you have a thin membrane and you can get the anode and cathode very close together. So people are looking at those hybrids. I think they're very interesting and certainly worth exploring as a technology, but they really are not as good as the pure water systems. If you can make the pure water systems work, they'd be much less expensive and easier to scale.